There was a time when Earth had no moon. The sky above the young planet was empty. The night sky was darker. The tides were weaker. The planet spun faster, completing a full rotation in only a handful of hours. And then something changed. Today, the moon drifts away from us by nearly 4 centimeters each year. It steadies our planet's tilt. It shapes the tides. It slows the length of our day. It feels permanent, but its existence is strangely improbable. Among rocky planets, a moon this large compared to its host is unusual. Its composition is even stranger. The moon is made of material remarkably similar to Earth's outer layers, yet it contains far less iron than our planet does. It does not look like something that simply formed nearby. It looks connected, but connected how? The early solar system was not peaceful. Large bodies moved in unstable paths. Worlds were still forming, surfaces melted and cooled, orbits shifted. Somewhere in that chaos, the Earth we recognize nearly ceased to exist in its current form, and yet from that instability, a companion emerged that would shape climate, oceans, and even the rhythm of our days. Was it an accident? Was it inevitable? Was it survival or near destruction? And if events had unfolded only slightly differently, would we be here at all? Tonight, we travel back to a sky without a moon and follow the evidence through heat, debris, and gravity to the moment Earth gained its silent companion. But before we begin, I'd love to know where in the world you're listening from tonight and what time it is there. I read all your comments, and they are one of my favorite parts of this sleepy little community. If you're enjoying these late night explorations, a like and a subscribe would mean a lot. So now take a deep breath, let your shoulders relax, and together, let's return to ancient Earth before the moon. Before the sky had a companion to trace its arc across the darkness, the young planet turned alone in a crowded field of debris. Around it, fragments of rock and metal circled the newborn sun, remnants of a system still assembling itself from dust and gravity. Earth had only just taken shape, gathering mass through countless collisions, its growing body heated by compression and impact until solid ground could not yet exist in any lasting form. About 4.5 billion years ago, this world was not blue, nor green, nor calm. It was a sphere of molten rock, radiant with internal heat. The energy from its formation remained trapped within, keeping its surface in a restless state. Instead of continents or basins, vast expanses of magma stretched in every direction, glowing beneath a thick and heavy atmosphere formed from vaporized minerals and volcanic gases. The horizon shimmered with rising heat, and any crust that briefly formed was quickly broken apart and melted again. Within this churning interior, gravity quietly began its work of separation. Dense elements, iron and nickel among them, drifted downward through the liquid layers. Over time, they gathered at the center, forming a metallic core that would later generate a magnetic field. Above that sinking mass, lighter silicate materials rose and pooled, creating the beginnings of a mantle and the first fragile surface layers. Differentiation was not gentle, but it was decisive. The planet organized itself from chaos into structure, even while its exterior remained volatile and unstable. The young Earth did not spin with the measured rhythm known today. Its rotation was swift, completing a full turn in perhaps 5 or 6 hours. Daylight and darkness alternated rapidly across the molten globe. This speed affected everything, from atmospheric circulation to the shape of the planet itself, which likely bulged more noticeably at the equator under the force of rotation. Time moved differently here, compressed into brief cycles of light and shadow that raced across a blazing surface. Impacts were frequent. Large bodies, some the size of mountains, and others rivaling small worlds, still crossed intersecting paths through the inner solar system. When they struck, they released staggering amounts of energy, adding further heat to an already molten environment. Each collision reshaped regions of the surface, sending plumes of vaporized rock high above the planet before gravity pulled the material back down in incandescent rain. Stability was temporary, always interrupted by another arrival from the surrounding debris field. There were no oceans yet. Water existed only as vapor within the atmosphere, or locked within minerals embedded in the mantle. Any liquid could not remain on the surface for long under such intense heat. Instead of waves, there were currents of molten stone, circulating slowly as convection carried heat from the depths upward. The planet's skin shifted and folded as internal forces sought release. Above this restless world, the sky was darker than the one now familiar. There was no large satellite to reflect sunlight into the night. Only distant stars pierced the haze, and the sun governed the days without interference. Without an external stabilizing presence, Earth's axial tilt may have wandered more freely over long spans of time, influenced only by the gravitational pull of other planets and the distribution of its own shifting mass. This was Earth before companionship, before tides shaped by anything beyond the sun, before a steady partner influenced its spin. It was a world assembling itself through heat and collision, organizing its interior while enduring a volatile exterior. The foundations of the planet were forming quietly within, even as the surface remained in motion, waiting for an event that would transform its isolation into something enduring. Silence did not define the early solar system. Motion did. Every direction held movement, every orbit carried uncertainty, and the space between the newborn planets was thick with remnants of their own creation. The sun had ignited only recently, and around it circled a flattened disk of debris, fragments left over from the collapse of a vast molecular cloud. Within that disk, gravity gathered dust into pebbles, pebbles into boulders, and boulders into bodies large enough to pull still more material toward themselves. Planets were not yet finished worlds. They were growing, reshaping, and clearing their paths. Each carried the scars of earlier collisions, and each moved through a region still crowded with rivals. The inner solar system, where rock and metal dominated over ice, was especially dense. Countless protoplanets, some approaching the size of Mars, traced overlapping orbits that occasionally intersected in slow, inevitable convergence. These encounters were not delicate. When two massive bodies met, the energy released dwarfed anything familiar in later ages. Rock did not merely crack, it flowed and vaporized. Crusts were torn away, mantles mixed. In some cases, smaller bodies were entirely absorbed, their material folded into the growing interiors of larger worlds. In other cases, collisions shattered both participants, scattering fragments outward to seed new impacts elsewhere. Accretion and destruction unfolded together as part of the same process. Mercury's large metallic core hints at a violent past, perhaps stripped of lighter layers by an enormous blow. Venus, nearly Earth's twin in size, likely endured similar upheavals that reset its surface again and again. Mars bears the imprint of colossal impacts that carved vast basins into its crust. Earth itself, still molten in parts, did not pass untouched through this era. Each of these planets was shaped not only by internal heat, but by the cumulative force of repeated planetary encounters. The debris field that filled their shared neighborhood was not static. Gravitational interactions constantly altered trajectories. A body nudged slightly by one close pass might find its orbit elongated, crossing the path of another world millions of years later. Small differences compounded over time, turning stable circuits into unstable crossings. The system adjusted gradually, though to an observer it would have appeared tumultuous and bright with repeated flares of impact. Asteroids were abundant, but they were not the only agents of change. Many of the collisions involved objects massive enough to rival entire planets. These were not minor strikes on a quiet surface. They were mergers, near misses, grazing encounters that transferred angular momentum and reshaped rotation rates. Each event subtly rewrote the architecture of the solar system. Orbits widened or contracted, axes tilted, periods of rotation sped up or slowed down, depending on the angle and energy of contact. Within this environment, chaos was not an exception, it was the background condition. Stability emerged slowly from repetition as larger bodies cleared their surroundings of smaller debris and established dominant gravitational zones. Over tens of millions of years, the number of wandering fragments declined. Surviving planets settled into more predictable paths, their violent growth giving way to longer phases of cooling and internal evolution. Yet during that formative window, no world existed in isolation. Each was vulnerable to interruption, subject to forces far beyond its own surface. The architecture of the present solar system carries the memory of those early collisions, encoded in planetary densities, spin rates, and orbital inclinations. What now appears orderly was assembled through impact and exchange, through countless encounters that left lasting imprints on every rocky planet circling the sun. Seen from a distance, the pairing almost feels symmetrical, a blue planet turning steadily, and beside it a pale sphere that seems, at first glance, modest in scale. Yet proportions in space can be deceptive. When measured carefully, the moon reveals itself as something far less ordinary than its quiet presence suggests. Its diameter is roughly 1/4 that of Earth. For a satellite orbiting a rocky planet, that fraction is strikingly large. If Earth were reduced to the size of a standard globe in a classroom, the moon would not be a tiny bead circling far away, but a companion substantial enough to command attention. The relationship is not one of planet and pebble. It is closer to a paired system, two bodies bound together in a gravitational conversation that neither fully dominates nor entirely escapes. Among the rocky planets of the inner solar system, no other example approaches this scale ratio. Mars possesses two small moons, irregular in shape and barely a trace in comparison. Mercury and Venus have none at all. In contrast, the gas giants host impressive retinues of satellites, some immense, but those planets themselves are so vast that even their largest moons remain small relative to their primary. Earth and its moon form a proportion unlike any other pairing among terrestrial worlds. That proportional weight carries consequences. The moon's gravity is strong enough to raise measurable tides across the entire globe, pulling at oceans, at the crust, even subtly at the atmosphere. Its presence shifts Earth's center of mass slightly outward from the geometric center of the planet, creating a shared barycenter around which both bodies revolve. This mutual motion is gentle and orderly now, but it reflects the substantial mass of the moon relative to Earth itself. Gravitational influence also extends to rotational dynamics. Over immense spans of time, tidal interactions have transferred angular momentum outward, gradually slowing Earth's spin while pushing the moon farther away. Such a mechanism requires not merely proximity but mass. A much smaller satellite would not exert the same persistent torque, nor would it imprint itself so clearly on the length of Earth's day. The scale of the moon allows it to shape planetary behavior in ways that seem disproportionate to its quiet glow. For scientists seeking to understand how moons form, these proportions became an early puzzle. Traditional models of satellite formation often relied on gradual accumulation from leftover material or the capture of a wandering object drawn in by gravity. Yet a captured body large enough to account for 1/4 of Earth's diameter would demand an improbable alignment of speeds and distances. Likewise, a gentle co-formation from the same local disk would be expected to yield compositions and densities more closely aligned with the planet as a whole, including its metallic core. The moon's size, therefore, stood as more than a numeric curiosity. It hinted that the story behind its origin could not be explained by simple analogy to other systems. Its mass was too significant, its gravitational partnership too influential, its proportional dominance too distinct among rocky worlds. Even before detailed chemical analyses or computer simulations matured, the raw geometry of Earth and Moon together suggested that something unusual had taken place in the deep past. In the steady light of modern observation, the pairing appears inevitable, as though no other arrangement could have existed. Yet the dimensions alone speak quietly of rarity. A satellite so large relative to its planet implies an origin shaped by forces not commonly repeated, an event capable of redistributing matter on a planetary scale and leaving behind a companion whose size continues to define the balance of an entire world. Long before modern simulations traced molten debris through digital space, the origin of the moon was approached with careful, almost patient imagination. Astronomers and physicists stood beneath the familiar glow in the night sky and attempted to reason backward, guided by gravity, motion, and the physical properties of rock and metal. Several ideas rose to prominence over the decades, each elegant in its simplicity, each eventually strained by the weight of new evidence. One of the earliest suggestions imagined the moon as a traveler. In this view, it began elsewhere in the solar system, moving independently through space until it passed close enough to Earth to be captured by gravity. The concept carried a certain narrative clarity, a wandering body drawn into permanent orbit, yet celestial mechanics is rarely so accommodating. For a capture to occur, a large amount of energy must be dissipated at precisely the right moment. Without some mechanism to slow the incoming object, it would either slingshot past Earth or collide directly with it. The moon's mass makes the scenario especially demanding. A body of that size cannot simply be snared without extraordinary conditions that leave clear traces. Over time, calculations showed that the odds of such a capture under realistic physical constraints were exceedingly small. Another proposal suggested that Earth and Moon formed together from the same local cloud of material. In this co-formation model, both bodies condensed side by side from a shared disk of debris, growing in tandem as the young solar system settled. At first glance, this explanation felt harmonious. Two companions born together from the same substance. However, as measurements of lunar rock chemistry improved, discrepancies emerged. The moon's overall density is lower than Earth's, indicating a relative lack of heavy metals such as iron. If both had formed from identical material in the same region, their internal compositions should more closely match. Instead, Earth possesses a large metallic core, while the moon's core is proportionally much smaller. The divergence hinted at a more selective process of formation than simple side-by-side growth. A third idea carried a more dramatic image. Known as the fission theory, it proposed that the early Earth, spinning rapidly, cast off a portion of its own outer layers. In this scenario, centrifugal forces from an exceptionally fast rotation flung molten material outward, which then coalesced into the moon. The Pacific Ocean basin was once speculated to mark the scar of this separation. Yet closer analysis revealed serious challenges. The angular momentum required for Earth to shed such a massive fragment would imply a rotation rate far beyond what even a young planet could likely sustain without disintegrating entirely. Furthermore, the distribution of mass and energy in the Earth-Moon system does not align neatly with what this model predicts. The physics could be adjusted only with assumptions that strained plausibility. As each theory was examined more closely, small inconsistencies accumulated into substantial gaps. The capture model faltered under the constraints of orbital mechanics. The co-formation idea struggled to reconcile compositional differences. The fission hypothesis demanded conditions that seemed incompatible with the stability of a forming planet. None could simultaneously account for the moon's size, its density, its orbital characteristics, and the shared chemical signatures embedded in lunar samples. These early attempts were not failures in spirit, but steps in refinement. Each theory sharpened the questions rather than dissolving them. The moon's presence above Earth remained steady and familiar, yet its origin resisted simple explanation. The evidence pointed towards something more complex, something capable of redistributing mass on a planetary scale, while leaving behind the particular proportions and compositions now observed. In the quiet accumulation of data, it became clear that any satisfying account would need to weave together dynamics, chemistry, and timing into a single, coherent event. In the quiet decades of the 20th century, as lunar samples were carried carefully into laboratories and examined grain by grain, a different kind of reconstruction began to take shape. Scientists compared isotopes, measured densities, and refined calculations that earlier generations could only approximate. Gradually, a new possibility surfaced, not from imagination alone, but from patterns hidden within stone. In the 1970s, several researchers proposed that the moon's origin might lie in a single, immense collision. Rather than capture, co-formation, or rotational shedding, they envisioned a far more forceful beginning. According to this emerging hypothesis, a body roughly the size of Mars approached the young Earth during its formative era. This object, later given the name Theia, likely occupied an orbit not far from Earth's own, moving through a region where gravitational interactions could slowly destabilize its path. Theia would not have been a minor intruder. A world of that scale carried substantial mass, enough to reshape another planet through direct contact. Its composition was probably similar to that of Earth's outer layers, a mixture of silicate rock and metal formed in the same inner region of the solar system. For some time, both bodies may have circled the sun in near resonance, separated by delicate balances of gravity. Over millions of years, those balances shifted. The collision that followed was not imagined as a simple head-on crash. Computer models and physical reasoning suggested something more oblique, a glancing encounter in which Theia struck Earth at an angle. In such a configuration, much of the impactor's core could merge with Earth's own metallic center, while vast amounts of lighter mantle material would be sheared away. The energy involved would have been extraordinary, high enough to melt large portions of both bodies and to loft streams of vaporized rock into surrounding space. This was not an explosion in the familiar sense, but a redistribution of planetary matter. As Theia's trajectory intersected with Earth's, angular momentum would be transferred between them, altering rotation rates and tilting axes. Layers of molten rock could have been peeled outward, forming an expanding cloud of debris encircling the battered planet. Some of this material would fall back under gravity, reabsorbed into Earth's growing mass. Some would escape entirely. A significant fraction, however, might remain in orbit, gradually spreading into a disk. The elegance of this hypothesis lay in its capacity to address multiple puzzles at once. A glancing impact could explain why the moon contains material chemically similar to Earth's outer layers, since much of that debris would originate from the mantles of the colliding bodies. It could also account for the moon's comparatively small metallic core if most of the dense iron from Theia sank into Earth during the merger. Even the unusual proportions of the Earth-Moon system, their shared angular momentum and relative masses, seemed consistent with such a dramatic exchange. As computational power increased in the late 20th and early 21st centuries, simulations grew more detailed. Digital models traced trajectories, mapped shock waves through molten interiors, and followed particles of debris as they circled the recovering Earth. While variations existed in the exact parameters, many scenarios converged on a similar picture: a single, massive, off-center collision giving rise to an orbiting ring from which the moon could eventually assemble. The giant impact idea did not arrive as a completed narrative, but as a framework capable of refinement. It offered a coherent way to integrate chemistry, dynamics, and scale into a unified account. Within this model, the moon's presence was not a gentle addition to Earth's history, but the outcome of a formative encounter between worlds, an event large enough to alter the architecture of the inner solar system while leaving behind a companion whose quiet light still carries the memory of that ancient exchange. Long before it had a name, it was simply another growing world circling the young sun. In the crowded inner solar system, material gathered wherever gravity allowed it, and among those gathering masses was a body that would one day be called Theia. It did not begin as an intruder. It formed from the same reservoir of rock and metal that shaped the terrestrial planets, condensing from dust and collisions into a sphere large enough to hold itself together. Its orbit was likely not far from Earth's own path. Some models suggest it may have emerged near one of the Sun-Earth gravitational balance points, regions where competing pulls briefly allow material to accumulate in relative steadiness. In such zones, a protoplanet could grow quietly for a time, sharing a similar distance from the Sun and moving in near rhythm with Earth. For millions of years, this arrangement may have appeared stable, two neighboring worlds separated by modest stretches of space, yet bound by similar trajectories. Theia's mass was substantial, perhaps comparable to that of Mars. A body of that scale would possess its own layered structure. Dense metals would settle toward its center, forming a core, while lighter silicate rock composed its mantle and surface. Internally, it would radiate heat from radioactive decay and residual energy of formation. Externally, its surface may have endured impacts from smaller debris, just as Earth and the other young planets did. It was not an anomaly, but a participant in the same formative processes unfolding across the region. Yet, gravitational balance in a developing planetary system is rarely permanent. Small perturbations accumulate. The influence of nearby planets, particularly massive ones still completing their own growth, could subtly shift orbital paths. Resonances build gradually, altering speeds and distances in increments too slight to notice in any single revolution, but significant across immense spans of time. A body sharing a near-Earth orbit would be especially sensitive to these interactions, pulled forward or slowed just enough to change its long-term trajectory. As these adjustments compounded, Theia's once steady course may have begun to drift. An orbit that was nearly circular could become slightly elongated. A comfortable separation could narrow. Each pass around the Sun would bring the two worlds into new configurations, their gravitational pulls tugging at one another in ways that altered their mutual alignment. Instability does not always arrive suddenly. Often it grows from the accumulation of subtle imbalances. In such an environment, convergence becomes increasingly likely. A protoplanet the size of Mars cannot simply vanish. Its mass ensures that any close approach exerts meaningful influence. If its path intersected Earth's orbit at the right moment, the outcome would be governed by momentum and geometry. There would be no intention in this meeting, no design, only the continuation of forces acting according to their laws. Theia, therefore, was not an alien outsider descending from the distant reaches of the solar system. It was a sibling world, born from similar material, evolving under the same young sun, shaped by comparable processes of differentiation and heating. Its destiny was intertwined with Earth's from the beginning, though neither body could perceive the inevitability of their shared future. The instability that eventually drew them together was embedded in the architecture of a system still arranging itself. In this quiet reconstruction, Theia becomes less a villain and more a consequence of celestial mechanics. A world of rock and metal, substantial and self-contained, formed in proximity to Earth and carried along by gravitational currents that slowly altered its path. Within the broader choreography of the early solar system, its movement toward instability was not extraordinary. It was simply another expression of the restless dynamics that shaped every planet during that era. Time narrows to a single alignment. In the vast sweep of orbital motion, there comes a moment when two paths cross in the same place, neither yielding. Roughly 4.5 billion years ago, such an alignment occurred between the young Earth and the world that had grown alongside it. Their convergence was not abrupt in the sense of surprise, but decisive in consequence. As Theia approached, gravity shaped the final geometry. Both bodies accelerated toward one another, drawn by mutual attraction that had been building quietly across earlier passes. The encounter was oblique rather than centered. Instead of a direct plunge, Theia struck Earth at an angle, its forward motion carrying it across the planet's outer layers in a sweeping collision that altered both worlds in a matter of hours. The energy released in that contact surpassed anything later history would ever witness. Entire regions of mantle material were subjected to pressures and temperatures high enough to melt and vaporize rock. Shock waves traveled through both interiors, compressing, heating, and redistributing matter. Portions of Earth's outer layers did not simply crack or fracture. They transformed, lifted outward in plumes of incandescent vapor and molten debris. Theia itself did not remain intact. Its outer rock was stripped away, mixing with material torn from Earth's mantle. The dense metallic core of Theia, propelled inward by momentum and drawn by gravity, plunged toward Earth's center. There it merged with the growing terrestrial core, adding mass and angular momentum to the interior. That fusion altered Earth's internal structure, enlarging the metallic heart that would later sustain a magnetic field. Meanwhile, above the collision site, matter that had once been part of two separate worlds expanded into space. Streams of molten rock and vaporized silicate arced outward, some following trajectories that would never return. Yet much of the ejected material remained gravitationally bound to Earth. Instead of dispersing entirely, it spread into an uneven, glowing disk encircling the wounded planet. In the immediate aftermath, Earth's surface was transformed once more into a global magma ocean. The impact had remelted crust and mantle alike, erasing any fragile structures that may have begun to stabilize. The atmosphere thickened with rock vapor, dense and luminous, reflecting the intense heat below. For a time, the planet would have resembled a world of fire and haze, its earlier evolution temporarily reset by the violence of the encounter. Within the encircling cloud, fragments collided and merged. Molten droplets condensed, clumped, and shattered again as gravity and angular momentum redistributed material along orbital paths. Some debris spiraled inward, raining back onto the molten surface. Some drifted outward, beyond Earth's gravitational hold. A substantial portion, however, remained in a narrow band where mutual attraction between fragments began to outweigh dispersal. The architecture of the Earth-Moon system was taking form even before the debris cooled. Angular momentum exchanged during the collision determined the distance and speed at which material orbited. The planet's rotation was altered, and its axis tilted relative to its orbit around the Sun. These new parameters would govern the long evolution that followed, from day length to seasonal pattern. What had begun as two neighboring worlds ended as one expanded planet, surrounded by a luminous ring. The merger of cores, the vaporization of mantles, and the launch of orbital debris were not separate stages but facets of a single transformative event. In the quiet of deep time, the violence condensed into structure. Earth carried within it the mass of Theia's heart, and above it revolved the scattered remnants of both bodies, suspended in a gravitational dance that would soon give rise to something enduring. In the aftermath, the planet did not shatter. It softened. Heat wrapped around the globe like a second atmosphere, penetrating every boundary that might once have held shape. Whatever fragile crust had begun to assemble before the collision was erased in hours, dissolved back into a luminous sea of molten stone. The surface became fluid from horizon to horizon. Rock, once layered and distinct, blended into a convecting ocean that moved with slow, powerful currents driven by internal heat. Vast plumes rose from deeper regions and spread outward before sinking again, carrying energy upward in a cycle that would persist for thousands of years. There were no continents, no rigid plates, no quiet landscapes. The entire exterior behaved as a single, restless mantle exposed directly to space. Above this incandescent ocean, the atmosphere thickened beyond recognition. The energy released by the impact had not only melted rock, but vaporized enormous quantities of it. Silicate vapor mingled with superheated gases, forming a dense envelope that glowed faintly under the reflection of sunlight. Clouds were not composed of water, but of mineral particles and droplets of condensed stone. Lightning may have flickered through this heavy sky, driven by charge imbalances within rising and falling plumes. Earth's shape itself may have shifted subtly under the redistribution of mass. Rotation, altered by the collision, influenced how molten layers settled. The equatorial region, already influenced by centrifugal force, could have bulged further as the magma ocean spread evenly around the core. Internally, the merging of metallic centers completed its quiet descent, with heavier elements continuing to migrate inward through the molten interior, reinforcing the planet's layered structure. The temperature at the surface would have been extreme, high enough to maintain rock in a molten state for extended periods. Cooling began immediately, radiating energy into surrounding space, yet the scale of the heated volume was immense. A thin, temporary crust might form in places where heat escaped more rapidly, only to fracture and founder back into the magma beneath. Stability arrived in brief episodes, then vanished. Within this global ocean of rock, chemical differentiation continued. Elements less dense than iron remained suspended in the upper layers, while heavier components sought deeper regions. Crystals could begin to form within the cooling melt, settling gradually and altering the composition of the residual liquid. This slow sorting influenced the mineralogy that would later define the first true crust once solidification became sustained rather than fleeting. The atmosphere, saturated with vaporized rock, also began a gradual transformation. As temperatures fell incrementally, silicate vapor condensed into droplets that rained downward into the molten sea. Each cycle of condensation and return reduced the density of the upper envelope. Over time, lighter volatile compounds, including water vapor released from the mantle, would accumulate above the heavier mineral gases, preparing the way for entirely different weather in ages still distant. From afar, Earth would have appeared as a brilliant ember against the darkness, its surface radiating heat into space, while encircled by a fading disk of debris left over from the collision. The glow was not uniform but mottled, shaped by convective patterns within the magma ocean. In this state, the planet carried no visible memory of its earlier surface features. It had been reshaped at a fundamental level. The molten phase was not an anomaly but a passage. The energy imparted by impact ensured that the young world passed once more through a stage of complete liquefaction before cooling could resume its patient work. In the depth of that global ocean, Earth reorganized itself again, carrying within it the merged core of a vanished neighbor, and above it the slowly evolving remnants that would soon begin to gather into a separate body. Above the newly molten planet, a halo of shattered stone traced a widening path through space. What had once been continuous layers of mantle now existed as countless fragments, droplets, and vapor condensates moving along intersecting orbits. The violence of impact had lifted them outward, but gravity did not release its hold so easily. Earth, though transformed, remained the dominant mass in the region, drawing much of the expelled material into a temporary embrace. The debris did not form a perfect ring at once. Initially, it was an uneven cloud, thicker in some regions, thinner in others, composed of matter moving at slightly different speeds and angles. Each fragment followed its own trajectory, governed by the balance between its outward momentum and Earth's inward pull. Some pieces traced elongated arcs that carried them far from the planet before curving back. Others settled into tighter loops, circling more rapidly within a compressed band. Collisions among fragments became frequent. Molten clumps struck one another, merging or shattering, depending on their relative velocities. Smaller droplets coalesced into larger masses as surface tension and gravitational attraction worked together. With each contact, energy was redistributed. Some collisions dampened motion, reducing eccentricity and encouraging fragments to settle into more uniform orbits. Others sent shards spinning off in new directions. Not all of the material remained captive. A fraction had been propelled with sufficient velocity to exceed Earth's escape threshold. Those fragments drifted away into independent solar orbits, becoming minor travelers in the broader system. Their departure subtly reduced the total mass of the ring, leaving behind a more tightly bound collection of debris. Meanwhile, another portion of the material followed inward spirals. Drag within the dense post-impact environment, along with gravitational perturbations, caused some fragments to descend, falling back into the incandescent ocean below in radiant streaks. Over time, the distribution of matter began to show patterns. Angular momentum imparted during the collision constrained much of the debris to a flattened plane around Earth's equator. Within this disk, mutual gravity between fragments became increasingly influential. As clusters grew, their gravitational fields strengthened, allowing them to draw in nearby material more effectively. The smallest particles were often swept up by larger bodies, clearing localized gaps that sharpened the structure of the ring. Cooling proceeded gradually. As fragments radiated heat into space, molten surfaces solidified, forming crusts over still warm interiors. Repeated collisions fractured these crusts, exposing fresh melt and promoting further merging. The process resembled a slow assembly, though driven not by intention but by the inevitable mathematics of attraction and motion. Within a few thousand years, the once chaotic cloud would have begun to narrow into a more coherent disk. Regions of higher density served as seeds around which additional material gathered. Each growing mass altered the local gravitational landscape, subtly redirecting nearby fragments into collisions that increased its size. In this way, the ring was sculpted by invisible forces, guided by the same gravitational principles that had drawn Earth and Theia together. From the surface of the cooling planet, if any vantage had existed to witness it, the sky would have been filled with luminous arcs. Glowing fragments would sweep overhead in steady procession, some faint, others bright, tracing curved paths against a backdrop of thinning vapor. The planet below remained molten and restless, yet above it order was beginning to emerge from dispersion. Gravity did not act suddenly. It shaped patiently, favoring accumulation over scattering wherever conditions allowed. In the narrowing band of orbiting stone, mass concentrated through repeated encounters. The debris ring, once a diffuse cloud of aftermath, was gradually reorganizing itself into something more cohesive, a structure poised on the threshold between fragmentation and unity. Within the narrowing disk, subtle differences in mass began to matter. What had once been a fairly even spread of fragments slowly developed regions of preference, places where slightly larger clumps exerted slightly stronger pulls. In a field governed by gravity, even a modest advantage can amplify over time. Small aggregates drew in neighboring particles, increasing their mass and strengthening their influence in quiet increments. Each encounter reshaped the balance. When two clumps met at moderate velocity, they tended to merge, their molten or partially solid interiors fusing into a single, larger body. Energy was released as heat, briefly softening surfaces and allowing material to redistribute before cooling again. Faster impacts sometimes fractured the participants, but even those fragments remained within the disk, available to be gathered once more. The environment favored accumulation rather than permanent loss. As centuries passed into thousands of years, a handful of growing bodies began to dominate their local neighborhoods. Their gravitational reach cleared nearby orbits, either by sweeping up smaller debris or by scattering it into different paths within the disk. This clearing effect created subtle gaps and lanes, sharpening the structure of the ring. Where mass concentrated, space became more defined. One of these growing aggregates gained a decisive lead. Positioned at a favorable distance from Earth, beyond the region where tidal forces would immediately tear a forming body apart, it occupied a zone of relative stability. There, repeated mergers added layer upon layer of material. Its surface, initially molten from the heat of accretion, radiated energy outward while new impacts replenished warmth from above. The growth was not instantaneous but persistent. With each passing orbit around Earth, the proto-moon traveled through a field of remaining debris, collecting smaller fragments like a slow gathering tide. The distribution of angular momentum ensured that material with compatible velocities was more likely to be retained, while incompatible fragments were deflected or absorbed by other, lesser aggregates. Gradually, the field simplified. Many minor bodies either merged into the dominant mass or were cast into decaying orbits that sent them inward. The forming moon occupied a position far closer to Earth than it does now. In those early epochs, it may have orbited at only a few tens of thousands of kilometers above the surface, looming large in the sky of the cooling planet. Its gravitational interaction with Earth was correspondingly strong, raising significant tidal bulges in the still soft outer layers below. The exchange of angular momentum had already begun, even as the new satellite continued to consolidate its own structure. Internally, differentiation likely occurred as well. Heat from accretion and radioactive decay allowed denser elements within the growing body to migrate inward, forming a modest core, while lighter silicates composed the bulk of its mantle and crust. The composition reflected its origins in the debris of mantles rather than cores, preserving a chemical kinship with Earth's outer layers. Over a span measured in thousands of years rather than millions, the debris disk thinned. The dominant body had consumed much of what remained in its orbital neighborhood. What once had been a luminous ring of scattered fragments coalesced into a single, coherent sphere, accompanied by sparse residual particles. The transformation from chaos to structure occurred through repetition, through countless small mergers guided by gravity. The moon was not assembled piece by piece in isolation, but grown from shared matter, shaped by the same forces that had orchestrated the collision itself. Formed much closer to Earth, still warm from its birth, it entered a gravitational partnership that would continue to evolve. In the quiet orbit of this new companion, the aftermath of impact began to take on enduring form. In laboratories far removed from the violence of early planetary history, small gray stones have been weighed, sliced, and examined under careful light. Within their crystals lie patterns that speak more quietly than any cratered surface. These patterns, traced through isotopes of oxygen, titanium, and other elements, reveal a remarkable kinship between the moon and the outer layers of Earth. Isotopes are subtle signatures, variations of the same element that differ slightly in mass. They behave almost identically in chemical reactions, yet their ratios preserve the history of the material from which they formed. When scientists compared lunar samples to rocks drawn from Earth's mantle, they found that many of these isotopic ratios align with extraordinary precision. The resemblance is closer than that seen between Earth and any other known body in the solar system. Such similarity suggests that both worlds share a common reservoir of material. This kinship extends beyond a single element. Oxygen isotopes, in particular, form a kind of planetary fingerprint. Meteorites from Mars and other parent bodies display distinct ratios, allowing researchers to distinguish their origins. Lunar rocks, however, cluster tightly with Earth's own values, as though shaped from the same molten source. The agreement is too consistent to dismiss as coincidence. It implies that the matter forming the moon was once intimately connected with Earth's outer layers. At the same time, differences remain that help refine the narrative. The moon's overall density is lower than that of Earth, indicating a smaller proportion of heavy metals, such as iron and nickel. Seismic measurements and analysis of the moon's moment of inertia point to a modest core relative to its total size. Earth, by contrast, possesses a large metallic core occupying a significant fraction of its radius. The contrast between the two bodies hints at a selective process during their separation. In the aftermath of the ancient collision, when mantles were stripped and cores descended, most of the densest material appears to have been retained by Earth. Theia's metallic heart, along with much of Earth's own iron, sank inward under gravity, merging into a deeper central region. The debris lofted into orbit consisted predominantly of lighter silicate material drawn from outer layers rather than from the metal-rich interior. As this material accumulated to form the moon, it carried with it the chemical signature of shared mantles, but lacked the concentrated metals locked within Earth's core. The result is a companion that resembles Earth not in its entirety, but in a specific aspect of its composition. The moon mirrors the planet's outer rock, the mantle that once flowed across a molten surface. It does not reflect the full internal layering of a differentiated world. This asymmetry aligns naturally with the physics of a glancing impact, where mantle material would be preferentially ejected while cores would tend to merge. Further subtleties appear in volatile elements, those that vaporize at lower temperatures. The moon is relatively depleted in certain volatiles compared to Earth, consistent with formation from hot debris exposed to intense heat and partial loss to space. These chemical traces reinforce a picture in which shared material experienced extreme conditions before settling into a new configuration. Taken together, the isotopic harmony and metallic disparity weave a coherent story. The moon's rocks carry the memory of Earth's mantle, preserved in crystalline form and carried back across space for study. Their chemistry speaks of closeness rather than capture, of separation within a shared molten environment rather than distant origin. In their quiet alignment of isotopes, they testify that the moon is not merely a neighbor but a remnant, assembled from matter that once belonged to Earth itself. Heat does not vanish all at once. It lingers, radiates, recirculates, and slowly surrenders to space. After the violence of merger and accretion, both Earth and its newly formed companion glowed with residual warmth, their surfaces shaped not by solidity, but by slow, luminous motion. Yet, even molten worlds are subject to patience. Over time, the balance between energy retained and energy released began to shift. The young moon, assembled from orbiting debris, retained intense internal heat from repeated collisions and compression. Its outer layers likely existed first as a global magma ocean, a churning expanse of molten silicate that enveloped the entire body. Within this ocean, minerals began to crystallize as temperatures gradually declined. Lighter crystals floated upward, forming an early crust composed primarily of anorthosite, a pale rock rich in plagioclase feldspar. Denser minerals sank toward the interior, contributing to the modest core and mantle beneath. This first crust was fragile, fractured repeatedly by impacts from lingering debris in the inner solar system. Yet with each episode of cooling, it thickened incrementally. Over millions of years, the moon transitioned from a molten sphere to a body with a solid exterior and a slowly cooling interior. Volcanic activity persisted for a time, filling low basins with darker basaltic flows that would later appear as maria across its surface. The outward signs of cooling were uneven, but the direction was clear. Earth followed a similar yet more complex path. Its greater mass allowed it to retain heat longer, and its internal layering was more pronounced. The global magma ocean that followed the collision began to radiate energy into surrounding space. As the surface temperature declined, a thin crust formed intermittently, breaking and reforming under convective currents beneath. With continued cooling, this crust grew more stable, insulating the interior while permitting gradual heat loss through volcanic and tectonic processes. Within Earth's thickening atmosphere, change unfolded more subtly. Water vapor released from the mantle and delivered by earlier impacts accumulated above the cooling surface. As temperatures fell below the boiling point of water, condensation began. Rain may have fallen for extended periods, its drops striking still warm rock and collecting in low regions. Over time, these waters pooled, forming the earliest oceans. Their presence marked a profound transformation, as liquid water stabilized surface chemistry and reshaped the planet's appearance. The interplay between crust formation and ocean condensation reinforced stabilization. Water interacting with newly formed rock-altered minerals, aiding in the development of more permanent continental fragments. Tectonic processes, driven by internal heat, began to organize the crust into moving plates, initiating cycles that would recycle material between surface and mantle. While the system remained dynamic, its changes followed patterns rather than upheaval. The gravitational partnership between Earth and Moon also entered a quieter phase. Tidal forces continued to exchange angular momentum, gradually adjusting rotation and distance, yet the extremes of early interaction softened as surfaces solidified. What had begun as a searing exchange of matter settled into a stable orbiting relationship, one that would persist across billions of years. This cooling did not erase the memory of impact, but refined it into structure. The moon acquired a permanent face marked by early craters and volcanic plains. Earth developed oceans and a resilient crust capable of sustaining chemical complexity. From molten beginnings emerged conditions that would allow entirely new processes to unfold. The era of constant liquefaction gave way to one of gradual shaping, where heat still flowed beneath the surface, yet stability increasingly defined the planetary landscape. Gravity does not need contact to leave its mark. It stretches, compresses, and gently reshapes from a distance, threading invisible lines between bodies that never touch. Once the moon settled into orbit, its presence became an active force in Earth's unfolding story, tugging at water, at crust, and at the slow turning of the planet itself. In those early ages, the moon circled much closer than it does today. Its gravitational pull was correspondingly stronger, and the tides it raised across the young oceans were far more dramatic. The water did not simply rise and fall by a modest margin, it surged. As Earth rotated beneath the orbiting moon, vast bulges of ocean water shifted across the globe, creating powerful cycles that reshaped shorelines again and again. These tides were not confined to narrow coastal strips. Because the moon orbited nearer, the gravitational gradient across Earth was steeper, amplifying the difference between the near side and the far side of the planet. Ocean basins may have experienced tidal ranges measured in many tens or even hundreds of meters. The movement was rhythmic, persistent, and energetic. Along the margins where water met newly solidified crust, the shoreline became a zone of constant transformation. Coastal regions expanded during high tides, flooding low areas and carrying dissolved minerals inland. As the water retreated, it left behind pools trapped in shallow depressions. These tidal flats formed broad transitional landscapes, alternately submerged and exposed within relatively short spans of time. Such repeated cycles encouraged mixing at multiple scales. Currents driven by tidal motion stirred the oceans vertically and horizontally, redistributing heat and chemical constituents. Nutrients carried from hydrothermal vents or weathered rock were transported into open water, while dissolved gases exchanged more readily between sea and atmosphere. The motion acted as a planetary pulse, blending ingredients that might otherwise have remained isolated. Chemical reactions are sensitive to concentration and environment. In shallow tidal pools, evaporation could increase the concentration of dissolved substances as water receded. When the next surge arrived, new material mixed with what remained, creating fluctuating conditions that favored experimentation at the molecular level. Although life had not yet emerged in these earliest epochs, the groundwork for complex chemistry was being laid through the steady cadence of tidal forces. The moon's influence extended beyond the water alone. Tidal flexing also acted subtly upon the crust and mantle. As the gravitational pull varied across Earth's surface, slight deformations occurred, dissipating energy as heat and contributing marginally to internal dynamics. These effects were not catastrophic but cumulative, integrating the orbital partnership into the planet's geologic rhythm. Over time, as the moon slowly migrated outward, the intensity of these tides diminished. Yet in the early era, their strength was a defining feature of Earth's environment. The interplay between rotation and orbit generated a repeating sequence of expansion and contraction, water advancing and withdrawing with dependable regularity. That regularity brought predictability to what had once been dominated by singular cataclysms. The gravitational relationship between Earth and Moon thus became more than a static alignment in the sky. It was a dynamic exchange, energy transferred incrementally, motion imposed across fluid surfaces. Through the Moon's steady pull, the oceans were kept in motion, their cycles carving patterns into coastlines and stirring the chemical sea. In the quiet persistence of those tides, the aftermath of collision was translated into a new kind of order, one measured not in impact, but in repetition. Rotation is not fixed in stone. It can change, though the change unfolds so gradually that it hides within deep time. After the moon settled into orbit, Earth did not continue spinning at the rapid pace it once possessed. The partnership between planet and satellite introduced a steady exchange, almost imperceptible in a single lifetime, yet profound across billions of years. In the earliest phase after formation, Earth turned swiftly, completing a full rotation in only a handful of hours. The aftermath of impact had left it energized and compact in motion. Yet the presence of the nearby moon created tidal bulges in the oceans and even within the pliable crust beneath. These bulges did not align perfectly with the line connecting the centers of Earth and Moon. Because Earth rotated faster than the Moon orbited, the tidal bulges were carried slightly ahead of the direct gravitational pull. This offset mattered. The bulges acted as gravitational handles, tugging subtly on the Moon as it passed. In response, the Moon tugged back on the displaced water and rock, creating a torque that slowed Earth's rotation by a tiny fraction with each passing orbit. The process did not halt the spin, but it diminished it incrementally, transferring rotational energy outward. Energy cannot disappear, only transform. As Earth surrendered a minute portion of its rotational momentum, that energy was converted into orbital motion for the Moon. The satellite gained a small amount of speed in its path around Earth, which caused it to shift to a slightly higher orbit. With each cycle of tides rising and falling, the distance between the two bodies increased by a measurable amount. The effect compounded over immense spans of time. What began as days measured in mere hours gradually stretched longer. Geological records, preserved in ancient sedimentary layers, reveal rhythmic patterns that reflect tidal cycles from hundreds of millions of years ago. These records suggest that in distant epochs, a year contained more days than it does now, each day slightly shorter. The lengthening continued, slow but persistent. As the moon moved farther away, the intensity of tidal forces decreased. Greater distance meant a weaker gravitational gradient across Earth's surface. The torque acting on the planet's rotation diminished correspondingly, leading to a gradual stabilization of the rate of change. Today, the extension of each day occurs by mere milliseconds per century, a subtle adjustment detectable only through precise instruments and long-term observation. The outward migration of the moon remains ongoing. Laser ranging experiments reflect beams off mirrors left on the lunar surface, measuring distance with extraordinary accuracy. These measurements confirm that the separation increases year by year, the orbit expanding as energy continues to flow from Earth's spin into the shared gravitational dance. This exchange illustrates the intimacy of celestial mechanics. The moon does not merely circle Earth as a passive companion, it participates in shaping the planet's temporal rhythm. The 24-hour day, familiar now, is the result of countless tidal cycles, each contributing an almost infinitesimal change. Over billions of years, those changes accumulated, transforming a rapidly spinning molten world into one with a measured cadence of light and darkness. Through this steady transfer, the Earth-Moon system evolved toward a quieter equilibrium. Rotation slowed, orbit widened, and the two bodies adjusted to one another in a continuing process. The slowing of Earth's spin was not abrupt, nor was it dramatic in any single moment. It was a gradual reshaping of time itself, guided by gravity and sustained through repetition. A planet does not spin upright, it leans. Earth turns upon an axis that is inclined by about 23.5 degrees relative to the plane of its orbit around the Sun. That quiet tilt, subtle in the scale of the globe yet profound in consequence, is what allows seasons to unfold, sunlight to shift across latitudes, and climate patterns to follow a rhythmic arc through each year. An inclined axis is not inherently stable. Left to itself, a rotating body can experience variations in tilt over long periods, influenced by gravitational tugs from neighboring planets and the redistribution of mass within its own interior. These variations, known as obliquity changes, can be modest or dramatic, depending on circumstances. The difference between a steady lean and a wandering one carries significant implications for surface conditions. Here, the moon's presence becomes decisive. Because it is relatively large compared to Earth, its gravitational influence extends beyond tides and rotation. It exerts a steady torque on Earth's equatorial bulge, that slight widening created by rotation. This interaction acts like a stabilizing weight, dampening the extent to which Earth's axis can wobble over immense spans of time. Rather than drifting through extreme angles, the tilt oscillates within a comparatively narrow range. Computer models that remove the moon from simulations of Earth's orbit reveal a different picture. Without the stabilizing torque of a substantial satellite, Earth's obliquity could vary far more widely. The axis might swing unpredictably, altering the distribution of sunlight in ways that generate intense and prolonged climate extremes. Periods of severe warming at one pole could alternate with deep cooling, reshaping atmospheric circulation and ocean currents on timescales shorter than geological systems might easily absorb. A nearby example offers perspective. Mars, though similar in many respects to Earth, lacks a large moon capable of exerting comparable stabilizing influence. Its two small satellites are too minor to meaningfully affect axial dynamics. As a result, models and geological evidence suggest that Mars has experienced significant changes in tilt across its history. Its obliquity may have shifted by tens of degrees, redistributing ice deposits and altering climate in pronounced ways. The Martian surface bears traces consistent with these variations, evidence of a planet whose lean has not remained tightly constrained. Earth's steadier tilt has supported long-term climate cycles that, while variable, follow patterns. The progression of seasons emerges reliably from the combination of axial inclination and orbital motion. Ice ages have come and gone, influenced by subtle variations in orbit and tilt, yet the underlying range has remained moderated. The presence of the moon does not eliminate change, but it tempers extremes. This stability matters for the continuity of surface processes. Ecosystems, atmospheric chemistry, and ocean circulation respond to climate patterns that evolve gradually rather than chaotically. Over billions of years, the damping of axial wobble has helped preserve conditions within bounds that allow complexity to persist. The tilt itself was likely influenced by the ancient collision, yet its continued moderation depends on the gravitational partnership that followed. The moon, distant and silent, contributes not only to visible tides and measured days, but to the orientation of the entire planet in space. Through its steady pull on the equatorial bulge, it restrains the wandering of Earth's axis. The lean of 23.5 degrees is not fixed beyond all possibility, yet it remains anchored within limits that have shaped the character of seasons. In this subtle balance between inclination and restraint, the architecture of long-term climate finds quiet support. There was a time when the moon dominated the sky in a way no living eye has ever witnessed. Newly formed and still orbiting much closer to Earth, it would have appeared enormous, spanning a far greater arc above the horizon than it does now. Its disk would have risen heavy and luminous, filling the night with a presence that felt almost immediate, as though the boundary between planet and satellite had narrowed. Because the distance between Earth and Moon was smaller, the apparent size of the moon in the sky was correspondingly larger. Angular diameter is governed by proportion, and in those early epochs the ratio favored spectacle. The moon's surface, still warm in places from its own recent formation, may have reflected sunlight, with subtle variations as volcanic plains and highlands continued to settle. Its proximity intensified both brightness and influence. Night, under such a moon, would not have resembled the darkness familiar today. Even without artificial light, the present moon can cast faint shadows and illuminate landscapes with a cool sheen. A closer moon would have done so more dramatically, raising the ambient glow of nighttime and altering the rhythms of illumination across newly forming oceans and crust. Shorelines shaped by powerful tides would have shimmered beneath a broader disk suspended above. Eclipses in this early era were more frequent as well. Because the moon orbited nearer to Earth, it crossed the sun's path from Earth's perspective more often, and its larger apparent size meant that total solar eclipses would have been particularly striking. The disk of the moon could fully envelop the face of the sun with a margin to spare, producing extended intervals of shadow across portions of the molten and then gradually cooling surface. Lunar eclipses would have unfolded with equal drama. When Earth's shadow reached the nearby moon, the transition into darkness would occur against a larger canvas. The reddish hues cast by refracted sunlight passing through Earth's thick early atmosphere might have painted its surface in deeper tones, enriched by the composition of gases and particles lingering above the planet. The sky itself looked different then, with the moon occupying a larger swath overhead and moving more swiftly through its orbit. The pattern of phases unfolded at a quicker cadence. Full moons, crescents, and shadows cycled more rapidly. Stars rising near the horizon would have shared space with a disk that seemed almost to press against the celestial background. As the moon gradually receded over millions and billions of years, these spectacles softened. The angular size diminished, eclipses shortened, and the brightness of night reduced incrementally. Today, the moon and sun appear almost precisely the same size in the sky, allowing for the delicate geometry of totality where the solar corona briefly reveals itself. In the distant past, that balance tilted in favor of the moon, its shadow more expansive and its presence more imposing. The early Earth sky was therefore not merely a stage for cooling crust and settling oceans. It was animated by a companion whose closeness reshaped light itself. The frequent alignment of sun, earth, and moon created recurring passages of shadow and brilliance. In those alignments, the aftermath of collision found expression in celestial choreography, marking time through light and dark as the two bodies settled into a partnership that would slowly evolve into the quieter balance seen now. Along the shifting margins where sea met stone, small basins formed almost by accident. Depressions in cooling crust, carved by earlier impacts or shaped by volcanic textures, became temporary reservoirs when tides retreated. Water gathered there, shallow and exposed to sky, then drained away as the ocean withdrew once more. These simple pools, repeated in countless variations along early coastlines, created environments distinct from the deeper sea. Within open oceans, dissolved minerals and simple organic molecules remained widely dispersed. Concentrations were often low, diluted by immense volumes of water. In tidal pools, however, evaporation during exposure could increase chemical density significantly. As water warmed under sunlight and thinned beneath the atmosphere, salts and other dissolved substances accumulated. Each return of the tide brought a fresh influx of materials, mixing new components with those left behind. This repeating cycle of concentration and dilution introduced a rhythm to chemical environments. Molecules formed in the depths could be carried into shallow pools, exposed to warmth, mineral surfaces, and fluctuating conditions. Clay minerals lining some pools may have provided catalytic surfaces, encouraging certain reactions to proceed more readily. In such settings, complex organic molecules could assemble from simpler building blocks under favorable conditions. Temperature variation also played a role. Shallow water responds more quickly to shifts in sunlight and air than does the open sea. Heating during exposure and cooling during submergence produced dynamic thermal cycles. Many chemical reactions depend on energy input, and periodic heating might have supplied pulses that enabled bonds to form, break, and rearrange. The repetition of these cycles allowed gradual refinement, favoring molecular combinations that were stable enough to persist through changing conditions. Some scientists suggest that these alternating environments offered advantages absent in permanently submerged habitats. In the depths, constant dilution could inhibit the concentration necessary for certain polymers to emerge. At the interface of land and sea, however, wet-dry cycles might assist in linking small molecules into longer chains, including precursors to nucleic acids and proteins. The formation of membranes, essential to compartmentalization, may also have been facilitated by periodic changes in salinity and temperature. The moon's gravitational pull ensured that tides were not random disturbances, but regular events. Strong early tides repeatedly flooded and exposed vast stretches of shoreline, multiplying the number of potential reaction sites. Instead of a static boundary between ocean and rock, there existed a broad, shifting zone that expanded and contracted with dependable cadence. It is important to recognize that this scenario remains a hypothesis. The exact pathway from chemistry to biology is still under investigation, and multiple environments have been proposed as possible cradles for life, including deep hydrothermal vents and ice-covered oceans. Yet, the tidal model carries persuasive features. It aligns the mechanical motion of celestial bodies with the microscopic assembly of molecules, linking gravity to the earliest experiments in complexity. In this view, the moon's influence extended beyond shaping oceans and stabilizing rotation. Through the steady rise and fall of tides, it may have created laboratory-like settings scattered across primordial coastlines. Within those shallow pools, chemistry had the opportunity to concentrate, to cycle, and to refine itself across millions of repetitions. Whether life ultimately began in such places cannot be stated with certainty, but the plausibility remains grounded in physics and chemistry working together under the patient guidance of tidal rhythm. deep beneath the oceans and continents, the mantle moves with a slowness that defies ordinary perception. Solid rock, subjected to immense pressure and heat, behaves over geological time like a thick fluid, rising in plumes and sinking in vast slabs. These convective motions drive plate tectonics, recycling crust, and reshaping the surface through earthquakes, mountain building, and volcanic arcs. The engine of this motion lies primarily in internal heat, yet some researchers have wondered whether the moon's steady pull contributes a subtle influence. Tidal forces do not act only on water. The gravitational attraction that lifts oceans also produces small deformations in the solid Earth. Twice each day, the planet's surface rises and falls by measurable centimeters as it responds elastically to lunar gravity. Over immense spans of time, such rhythmic flexing might seem capable of introducing additional energy into the mantle system. The idea is not that tides power plate tectonics outright, but that they could modulate or slightly enhance existing motions. In models exploring this possibility, tidal stresses are examined as a periodic input layered upon the mantle's convective circulation. The moon's pull creates patterns of stress and strain that vary with Earth's rotation and orbital geometry. Some researchers propose that these variations might influence the timing of certain tectonic events, perhaps nudging fault systems closer to failure or affecting the ascent of magma along specific pathways. Others consider whether early, stronger tides, when the moon was nearer, could have had a more pronounced impact on the mantle's behavior. Yet the evidence remains mixed. The energy budget of plate tectonics is dominated by internal heat from radioactive decay and residual formation energy. Compared to this vast reservoir, tidal energy dissipated within the solid Earth is relatively small. Measurements of heat flow and mantle dynamics suggest that while tidal friction contributes to localized heating, it is unlikely to serve as a primary driver of large-scale convection. Computer simulations incorporating tidal stresses often show only subtle modifications to patterns already governed by thermal forces. Geological records provide limited clarity. While some studies have searched for correlations between tidal cycles and earthquake frequency, the results are not consistent across regions or timescales. Tectonic plates move at rates measured in centimeters per year, guided by forces originating deep within the mantle. Isolating a clear signature of lunar influence amid such complexity proves challenging. The debate highlights the difficulty of disentangling interacting processes within a dynamic planet. Earth is not shaped by a single mechanism, but by layered influences operating simultaneously. Gravity from the moon, solar radiation, internal heat, and the distribution of mass all intersect in subtle ways. Determining the extent of each contribution requires careful modeling and increasingly precise measurements. Some researchers suggest that in the earliest epochs, when the moon orbited closer and tidal forces were stronger, the cumulative effect on mantle dynamics might have been more noticeable. Others argue that even under those conditions, the dominant source of tectonic motion would still have been internal heat. The question remains open, not because of a lack of effort, but because the system under study is intricate and multifaceted. This ongoing discussion reflects the nature of scientific inquiry. Hypotheses are proposed, tested, revised, and sometimes set aside as new data emerges. The moon's role in shaping tides, rotation, and axial stability is well supported. Its influence on plate tectonics, however, occupies a quieter and more uncertain space within planetary science. In that uncertainty lies an acknowledgement of complexity, a recognition that even a companion as constant as the moon may still hold aspects of its partnership with Earth that are not yet fully understood. When human hands first lifted lunar stone from the surface and sealed it inside protective containers, the material carried more than dust and basalt. It carried a timeline. The samples returned during the Apollo missions were small in size but vast in implication, fragments of a world that had preserved its early history with unusual clarity. Between the late 1960s and early 1970s, astronauts collected and transported hundreds of kilograms of lunar material back to Earth. These rocks, gathered from Maria Plains and highland regions alike, were cataloged and distributed to laboratories around the world. Within clean rooms and under precise instruments, scientists began to examine their mineral content, crystal structure, and isotopic composition in careful detail. Radiometric dating techniques provided one of the first anchors in time. By measuring the ratios of parent and daughter isotopes in minerals such as zircon and plagioclase, researchers could estimate when the rocks solidified. Many samples yielded ages close to 4.5 billion years, placing their formation very near the dawn of the solar system. This antiquity supported the idea that the moon emerged shortly after Earth itself, rather than forming much later through capture or gradual accumulation. Textural evidence within the rocks told an additional story. Basalts collected from dark plains displayed features consistent with volcanic origin, formed from molten material that had once flowed across the lunar surface before cooling. Highland samples, composed largely of anorthosite, suggested flotation of lighter minerals within an early global magma ocean. Together, these characteristics aligned with a history that included large-scale melting and differentiation. The absence of abundant, volatile elements within many lunar samples offered further clues. Compared to Earth, the moon's rocks are relatively depleted in substances that vaporize easily. This depletion is consistent with formation under high-temperature conditions, where lighter components would have been partially lost to space during or after a massive impact. The mineralogy reflected exposure to intense heat, reinforcing the hypothesis of a violent beginning followed by widespread melting. Isotopic analyses deepened the connection between Earth and Moon. Oxygen isotopes within lunar minerals matched Earth's mantle values with striking precision, a detail difficult to reconcile with capture scenarios. Titanium and other isotope systems exhibited similar alignments. These parallels indicated that the material composing the moon did not originate in a distant region of the solar system with a distinct isotopic fingerprint. Instead, it shared a common source with Earth's outer layers. Seismic experiments conducted on the moon, using instruments left by astronauts, revealed internal structure consistent with a differentiated body possessing a relatively small core. This finding complemented geochemical measurements, confirming that dense metals are less prevalent within the moon than within Earth. The pattern matched expectations derived from models in which most iron-rich material had merged into Earth during collision, while lighter silicates were lofted into orbit. Each rock examined contributed a fragment of evidence. None alone proved a single theory beyond doubt, yet collectively they formed a coherent narrative. Ancient crystallization ages, signatures of a molten past, chemical depletion patterns, and isotopic kinship converged on an origin involving shared material subjected to extraordinary heat. The moon's surface, unaltered by active plate tectonics or extensive erosion, preserved this record with uncommon fidelity. In its stones, brought across space by human effort, the early conditions of the Earth-Moon system remain accessible. Through laboratory analysis, The quiet testimony of those rocks continues to refine our understanding of how two worlds became bound together in the aftermath of cosmic upheaval. In rooms filled not with rock, but with processors and light, scientists began to reconstruct the ancient collision through mathematics. Equations replaced craters, and coded algorithms traced the motion of molten worlds across digital space. Where laboratory samples offered chemistry and age, computer simulations provided motion and sequence, allowing researchers to rewind the solar system and explore possibilities step by step. Early models were limited by computational power. Simplified calculations treated planets as uniform spheres and approximated collisions with broad assumptions. Even so, these initial simulations hinted that a glancing encounter between a young Earth and a Mars-sized body could produce a disk of debris rather than total destruction. As computing capacity expanded, so too did the sophistication of the models. Modern supercomputers can divide colliding planets into millions of discrete particles, each governed by gravitational forces, pressure equations, and thermodynamic constraints. Using a method known as smooth particle hydrodynamics, researchers simulate how shock waves propagate through planetary mantles, how cores merge, and how material is lofted into orbit. Each particle carries properties of mass, velocity, temperature, and composition, evolving in response to its neighbors. In many simulations, when a body the size of Theia strikes Earth at an oblique angle, the outcome aligns closely with observed evidence. Much of the impactor's core descends toward Earth's center, merging with the terrestrial core. Surrounding mantle material from both bodies is ejected outward, forming an expanding cloud that settles into a circumplanetary disk. Within this disk, density patterns emerge that allow a substantial moon to accrete over time. Crucially, simulations also track angular momentum. The total angular momentum of the Earth-Moon system today is measurable, and any successful model must reproduce it. The transfer of momentum during impact influences Earth's rotation rate and the orbital speed of the debris. If the simulated collision imparts too much spin, the resulting system differs from reality too little, and it cannot account for the Moon's current orbit. Iterative modeling refines impact angles, velocities, and masses to achieve consistency with known constraints. As models have grown more detailed, variations on the original hypothesis have been explored. Some suggest a single, large impact, while others test scenarios involving multiple smaller collisions. A few high-energy models examine nearly vaporized Earths, where much of the debris forms from a shared, partially vaporized envelope. Each iteration is assessed against isotopic data, lunar mass, orbital distance, and rotational dynamics. Despite increasing precision, simulations remain approximations. They depend on assumptions about material properties under extreme pressure and temperature, regimes difficult to replicate experimentally. Differences in initial conditions can lead to divergent outcomes. Researchers adjust parameters, compare results, and refine their codes as new observational data becomes available. The strength of these digital reconstructions lies not in producing a single definitive animation, but in narrowing the range of plausible histories. By running countless scenarios, scientists identify configurations that yield a moon-matching observed mass, composition, and orbital characteristics. Improbable pathways are discarded. Consistent ones are examined more closely. Computational modeling continues to evolve as hardware improves and algorithms become more efficient. With each advance, the simulated early solar system grows more nuanced, revealing interactions once too complex to calculate. In this quiet interplay between mathematics and memory, the ancient collision is replayed again and again, not as spectacle but as an evolving hypothesis, shaped by data and constrained by physics, gradually approaching a history that aligns with the world we inhabit today. Scientific ideas rarely remain fixed in their first form. Once a framework begins to explain observations, it invites refinement, variation, and challenge. The giant impact concept provided a powerful starting point, yet over time, researchers have explored multiple versions of how such a collision might have unfolded, adjusting parameters to better match the growing body of evidence. The earliest widely accepted scenario envisioned a single, large impact between the young Earth and a Mars sized body. In this model, the angle and velocity were calibrated so that mantle material was expelled into orbit while cores merged. It accounted for the Moon's size, its relatively small metallic core, and the angular momentum of the Earth-Moon system. For many years, this single impact configuration stood as the leading explanation, supported by computer simulations and geochemical data. As isotopic measurements became more precise, however, subtle complexities emerged. Some analyses indicated an even closer match between lunar and terrestrial isotopic signatures than certain single impact models predicted. If a significant portion of lunar material originated primarily from the impactor, slight differences might be expected. To address this, researchers began considering variations that would produce more thorough mixing between Earth and the colliding body. One such variation proposed a higher energy collision, sometimes referred to as a synestia model. In this scenario, the impact is energetic enough to partially vaporize both bodies, creating an extended, rotating cloud of rock vapor enveloping Earth. Within this structure, material from both progenitors becomes thoroughly mixed before cooling and condensing. As the system contracts, a satellite forms from this shared envelope, inheriting isotopic similarity from a fully blended source. These high-energy models offer an elegant way to reconcile near identical isotopic compositions, though they depend on extreme initial conditions. Another alternative considers multiple smaller impacts rather than a single decisive event. In this framework, Earth experiences a sequence of substantial collisions during its early history. Each impact contributes debris that may form a temporary moonlet. Over time, these smaller satellites merge or fall back to Earth, gradually building a larger moon through cumulative accretion. This approach distributes the formation process across several episodes, potentially allowing more thorough mixing of material between Earth and impactors. Each of these variations must still satisfy constraints imposed by observable data. The total mass of the Moon, the present angular momentum of the Earth-Moon system, the composition and depletion of certain volatile elements, and the age of lunar rocks all serve as benchmarks. Simulations are tuned to explore different combinations of impact, angle, velocity, mass ratio, and thermodynamic behavior. When a variation aligns with multiple lines of evidence, it gains attention. When it fails to meet key criteria, it is adjusted or set aside. The process of refinement reflects the evolving nature of scientific understanding. No model is accepted solely for narrative simplicity. Each must withstand comparison with increasingly detailed measurements and computational reconstructions. As laboratory techniques improve and new lunar samples are analyzed, the boundaries within which viable scenarios can operate become narrower. The core idea that the Moon arose from a major collision remains robust. What continues to shift are the specifics, the degree of mixing, the number of impacts, and the energy involved. These adjustments do not weaken the overarching framework, but rather sharpen it. In the interplay between observation and theory, the ancient event is revisited repeatedly, its contours refined with each generation of inquiry, drawing ever closer to a history consistent with both physics and stone. Outcomes in celestial mechanics depend not only on force, but on angle, speed, and timing. When two planetary bodies converge, small variations in trajectory can produce profoundly different results. The collision that ultimately led to the moon's formation did not exist in a realm of inevitability. It unfolded within a narrow band of physical conditions where destruction and creation met in delicate proportion. Had the impact been more direct, with Theia striking head-on rather than at an angle, the consequences could have been far more severe. In such a scenario, the energy delivered would have penetrated deeper into Earth's interior, potentially disrupting the planet beyond recovery. Instead of a glancing exchange that redistributed mantle material into orbit, a central collision might have resulted in a merged body with insufficient debris to form a substantial satellite. In extreme cases, simulations suggest that too direct an impact could have led to a more complete mixing of both bodies, erasing distinct layers and leaving behind a hotter, more homogenized planet without the stable orbital system that eventually emerged. Conversely, if the collision had been too small in scale, the outcome would have been equally transformative in a different way. A body significantly smaller than Mars would lack the mass required to loft enough material into sustained orbit. The debris might disperse temporarily, forming a faint ring that gradually spiraled back to Earth's surface. Without a sufficient volume of silicate matter remaining beyond the Roche limit, no dominant moon could accrete. Earth would cool and evolve alone, without the gravitational partner that later influenced tides, rotation, and axial stability. Velocity also played a critical role. If Theia approached too slowly, the energy imparted during contact might not have been enough to propel material into stable orbit. Debris ejected upward would arc outward briefly before falling back, drawn once again by Earth's gravity. The redistribution of angular momentum necessary to establish the present Earth-Moon system would not occur. The planet might experience intense melting and internal restructuring, yet no enduring satellite would remain. At the opposite extreme, a collision at excessively high velocity could result in more material escaping the system altogether. Rather than forming a coherent disk, fragments might disperse into independent solar orbits. The balance between retention and escape required a specific range of speeds and angles, sufficient to eject mantle material beyond immediate reabsorption, but not so forceful as to disperse it irretrievably. Computer simulations, exploring thousands of parameter combinations, reveal that the successful formation of a moon with current mass and orbital properties occupies a relatively narrow corridor of possibilities. The impact angle must allow for shearing rather than direct penetration. The mass ratio must be large enough to generate substantial debris, yet not so overwhelming as to destabilize the merged planet. The velocity must fall within limits that produce a bound disk while preserving the angular momentum observed today. These sensitivities highlight the contingent nature of planetary evolution. The Earth-Moon system is not merely a product of collision, but of a collision that occurred under conditions neither too violent nor too modest. In that precise calibration of angle, mass, and speed, matter was rearranged into a configuration capable of long-term stability. From deep time's perspective, the event appears singular and resolved, yet within the equations that describe gravitational encounters, alternate outcomes remain visible. A slightly different trajectory, a marginally altered velocity, and the architecture of Earth's future could have diverged profoundly. The moon's existence rests within that narrow band where chaos aligned with constraint, allowing debris to gather rather than vanish, and ensuring that the aftermath of impact became a companion rather than an absence. Stability in planetary systems often depends on subtle balances that are easy to overlook. Earth's seasons, so familiar in their rhythm, arise from the tilt of its rotational axis relative to its orbit around the Sun. That tilt, a little over 23 degrees, determines how sunlight shifts across latitudes over the course of a year. Yet axial tilt is not fixed by rotation alone. It can drift, oscillate, and in some circumstances vary dramatically over geological time. The moon exerts a stabilizing influence on this tilt. Through gravitational interaction, it dampens larger swings in Earth's obliquity, keeping variations within a relatively narrow range. Without such a companion, theoretical models suggest that Earth's axis might wander far more chaotically. The gravitational tugs of other planets, particularly Jupiter, would still act upon Earth. In the absence of a sizable moon to moderate these effects, the axial angle could fluctuate by tens of degrees over millions of years. A wider range of tilt would translate into more dramatic climatic consequences. When axial tilt increases, polar regions receive more direct sunlight during their respective summers and far less during winters. When tilt decreases, seasonal contrasts diminish, and high latitudes receive consistently low solar input. Large swings between these states could intensify climatic cycles, amplifying periods of glaciation and melting beyond the patterns Earth has historically experienced. Ice ages already form part of Earth's natural variability, influenced by orbital parameters and atmospheric composition. Without a stabilizing moon, those cycles might become more extreme or less predictable. Polar ice sheets could expand farther toward the equator during certain epochs, reflecting more sunlight and reinforcing global cooling. During other intervals, heightened tilt could produce intense summers that accelerate ice loss, altering sea levels and reshaping coastlines. These fluctuations, unfolding over immense timescales, would affect ocean circulation, atmospheric dynamics, and the distribution of ecosystems. Climate stability plays a significant role in long-term habitability. Life can adapt to gradual change, but persistent and severe oscillations pose greater challenges. If Earth's axial tilt were to vary unpredictably between relatively small and very large angles, environments could shift more abruptly on geological scales. Regions that once experienced moderate climates might periodically endure conditions far outside their typical ranges. The biosphere would need to reorganize repeatedly in response. Comparative planetology offers a useful reference point. Mars, lacking a large moon, exhibits greater variation in axial tilt over time. Its obliquity can shift substantially, contributing to climatic changes that alter the distribution of ice and potentially the stability of surface water in its early history. While Mars differs from Earth in many respects, the contrast illustrates how the presence or absence of a substantial satellite can influence axial behavior. It is not certain that the absence of the moon would render Earth uninhabitable. Internal feedback mechanisms within the climate system, including greenhouse gas regulation and ocean heat transport, might buffer some extremes. Yet models indicate that the range of possible conditions would widen. Habitability would become less predictable, subject to broader swings in seasonal intensity and glacial cycles. In this light, the moon's role extends beyond shaping tides and eclipses. Through its gravitational partnership, it acts as a quiet moderator of Earth's axial orientation. The regularity of seasons and the relatively bounded nature of climatic variation across deep time reflect an interplay between celestial mechanics and planetary atmosphere. Remove that stabilizing influence, and the balance shifts. The resulting world would follow a different climatic cadence, one where long term stability is less assured and environmental rhythms are written with a more variable hand. Each night, when the moon rises above the horizon, it presents a familiar pattern of light and shadow. Dark plains stretch across one hemisphere, while brighter highlands frame their edges. This face has become so constant that it feels like a fixed emblem in the sky, yet its stillness is the result of a long process shaped by gravity and time. The moon is tidally locked to Earth. It rotates on its axis at the same rate that it orbits our planet, completing one rotation in the same interval required for one orbit. This synchronous motion ensures that the same hemisphere continually faces Earth, while the far side remains hidden from direct view. Tidal locking emerged gradually. In the distant past, friction within the moon's interior dissipated rotational energy as Earth's gravity raised tidal bulges on its surface. Over countless cycles, this friction slowed the moon's original rotation until equilibrium was reached. Although one hemisphere is permanently turned toward Earth, the view from our planet is not entirely static. A subtle motion known as libration allows observers to glimpse slightly more than half of the lunar surface over time. Variations in orbital eccentricity and axial tilt create gentle shifts in perspective, revealing edges that would otherwise remain beyond sight. Still, the dominant impression remains constancy, a steady companion whose face rarely changes. The relationship between Earth and Moon continues to evolve. Laser ranging experiments, which bounce beams off reflectors placed on the lunar surface, have measured the distance between the two bodies with remarkable precision. These measurements confirm that the moon is slowly receding from Earth at a rate of several centimeters per year. The cause lies in the ongoing exchange of angular momentum. As Earth rotates, tidal bulges raised by the moon are carried slightly ahead of the line, connecting both bodies. The gravitational interaction between these displaced bulges and the moon transfers rotational energy outward, nudging the moon into a slightly higher orbit. This gradual recession lengthens Earth's day by tiny increments. The process is slow, unfolding over millions of years, yet it is measurable. Fossil records and growth bands in ancient corals indicate that days were shorter in the distant past, reflecting a faster rotation. The present configuration is not permanent, but part of a continuing dynamical evolution. Looking far ahead, models suggest that this exchange will persist. The moon will drift farther outward, and Earth's rotation will continue to slow. Eventually, the system may approach a state where both bodies are mutually tidally locked, each showing the same hemisphere to the other. Such equilibrium lies in a future measured not in centuries, but in astronomical spans of time. Despite this quiet motion, the moon today appears stable and enduring. Its surface bears the marks of ancient impacts, preserved in a landscape largely unchanged by weather or plate tectonics. From Earth, its phases mark the passage of weeks. Its brightness shapes nocturnal illumination, and its presence anchors cultural and scientific imagination alike. What we observe now represents a midpoint in an ongoing story. The moon is neither as close as it once was, nor as distant as it will become. Bound by gravity, yet slowly moving away, it continues to influence Earth in subtle but persistent ways. In this steady exchange between rotation and orbit, the present state of the Earth-Moon system unfolds as part of a larger arc, extending backward to impact and forward into deep time. Time moves differently on a planetary scale. What appears fixed within a human lifetime is, in celestial terms, still in motion. The moon's slow retreat continues, measured in centimeters each year, a pace so gentle it escapes ordinary perception. Yet across tens of millions and then billions of years, that incremental drift reshapes the architecture of the Earth-Moon system. As the moon moves farther outward, the exchange of angular momentum persists. Earth's rotation gradually slows, lengthening the duration of a day by fractions of a second over long intervals. Fossilized growth patterns have already shown that ancient days were shorter, and this trend will continue. Oceans will respond to a slightly longer rotational cycle, and atmospheric circulation will subtly adjust to new timing between heating and cooling. With increasing distance, the moon's gravitational pull on Earth's oceans will weaken. Tides, once towering in the planet's youth, are already gentler than they were billions of years ago. In the far future, their amplitude will diminish further. Coastal margins will still experience the rise and fall of water, but the energetic mixing that once characterized early shorelines will soften. The slowing of tidal forces also reduces the rate at which rotational energy transfers outward, making the recession itself progressively more gradual. Given enough time, models suggest that Earth and Moon could approach a mutual tidal lock where both bodies rotate in synchrony, each showing a fixed hemisphere to the other. In such a configuration, one side of Earth would continually face the Moon, while the opposite side would never see it. This equilibrium would represent a final stage in their gravitational dialogue, though reaching it would require spans of time extending beyond several billion years. Yet the distant future of the Earth-Moon relationship cannot be considered in isolation from the broader evolution of the Sun. Stellar physics indicates that our Sun will gradually increase in luminosity over geological time. Even within the next billion years, incremental brightening may alter Earth's climate significantly, potentially affecting the stability of oceans and the carbon cycle. Farther ahead, in roughly 5 billion years, the Sun is expected to expand into a red giant phase, dramatically transforming the inner solar system. During that expansion, solar radiation and mass loss will reshape planetary orbits and thermal environments. Earth's surface conditions may become inhospitable long before any final tidal equilibrium is reached. Oceans could evaporate under intensified solar output, and atmospheric chemistry may shift beyond recognition. The Moon, continuing its outward drift, would remain gravitationally bound unless perturbed by larger systemic changes, yet the context of its orbit would be profoundly altered. These projections emphasize that planetary systems evolve on multiple interacting timescales. The slow outward migration of the Moon unfolds alongside internal geologic processes and stellar transformation. No single trend proceeds independently. Each influences and is influenced by broader dynamics. What endures through these changes is motion itself. The Earth-Moon pair, born from collision, continues in quiet adjustment. Days lengthen imperceptibly, tides soften, distances widen. Beyond that, the Sun's life cycle imposes its own arc, gradually redefining conditions for every orbiting body. In contemplating the distant future, one encounters not a fixed endpoint but a continuum of change. The Moon will not remain exactly as it appears tonight, nor will Earth's rotation or climate remain static. Instead, the system drifts forward through gravitational exchange and stellar evolution, its current balance only a temporary arrangement within a far longer celestial narrative. Understanding does not arrive as a finished sculpture. It is shaped gradually, trimmed and revised as new tools reveal subtler details. The story of the Moon's formation, though supported by strong evidence, remains open to refinement because science itself advances through continual testing and revision. Early hypotheses relied on limited data, fragments of rock, and broad physical reasoning. With each decade, analytical techniques have grown more precise. Isotope measurements, once restricted by instrumental resolution, now detect variations at levels previously indistinguishable. Oxygen, titanium, tungsten, and other isotopic systems provide increasingly fine fingerprints of planetary material. As measurement uncertainty narrows, models must adjust to account for even slight discrepancies. These refinements do not dismantle the overarching framework of a giant impact. Rather, they sharpen its contours. When isotopic ratios between Earth and Moon appear nearly identical, researchers examine mixing processes with greater care. When small anomalies arise, they explore whether those differences reflect contributions from an impactor, post-impact alteration, or sampling limitations. Each new data set prompts recalibration of assumptions embedded within earlier simulations. Lunar missions also continue to expand the available evidence. Past expeditions sampled limited regions of the near side. Future missions, including robotic landers and orbiters, target previously unexplored terrains such as polar regions and the far side. These areas may contain materials that preserve distinct episodes of lunar history. By analyzing fresh samples, scientists hope to constrain the timing of crust formation, magma ocean crystallization, and impact basins more precisely. Remote sensing instruments add another layer of insight. High-resolution spectroscopy from orbit identifies mineral distributions across vast swaths of the surface, revealing compositional heterogeneity that ground samples alone cannot capture. Gravity mapping exposes subtle internal structure, refining estimates of core size and mantle thickness. Together, these observations feed back into impact models, testing whether simulated outcomes align with the Moon's current architecture. Advances in computational power further contribute to refinement. Modern simulations incorporate improved equations of state that describe how rock behaves under extreme pressure and temperature. They model vaporization, phase transitions, and material mixing with greater fidelity than earlier approximations. With enhanced resolution, subtle effects that once went unnoticed can now be evaluated directly. As a result, scenarios previously considered viable may require modification, while new possibilities emerge within tightened constraints. Unresolved questions remain. The exact degree of mixing between Earth and the impactor is still debated. The thermal state of the disk that formed the Moon continues to be modeled with evolving assumptions. The relative timing between impact and final accretion is constrained, but not defined to absolute precision. These uncertainties are not signs of weakness. They reflect the complexity inherent in reconstructing an event that occurred more than 4.5 billion years ago. Scientific refinement thrives on convergence. When independent lines of evidence, geochemistry, orbital dynamics, seismic data, and simulation outputs align within narrowing bounds, confidence strengthens. When discrepancies appear, investigation deepens. The story grows clearer not by closing inquiry but by sustaining it. The Moon's origin remains one of planetary science's most compelling reconstructions. Its broad narrative arc stands firm, yet its details continue to be shaped by new data and evolving methods. In laboratories, observatories, and mission planning rooms, the dialogue between evidence and theory persists, gradually clarifying how chaos once reorganized into the steady companion that now circles Earth. Across the solar system, moons are not unusual. They accompany planets, in a wide range of sizes, compositions, and orbital patterns. Some drift like irregular stones caught in gravity's net, while others form intricate systems of resonant orbits. Yet, when these satellites are compared carefully, Earth's moon occupies a distinctive place among them. Mars offers a useful contrast. It possesses two small moons, Phobos and Deimos, each irregular in shape and modest in size. Their surfaces are heavily cratered, and their appearance resembles captured asteroids. Their masses are tiny compared to Mars itself, and their gravitational influence on the planet is minimal. Phobos is gradually spiraling inward and may eventually break apart or collide with Mars. These companions, though intriguing, do not dominate the Martian sky in the way our moon dominates Earth's. Beyond the inner solar system, the gas giants host expansive families of satellites. Jupiter, Saturn, Uranus, and Neptune each retain dozens of moons, ranging from small, irregular bodies to large, differentiated worlds. Some, like Ganymede and Titan, rival or exceed the size of Mercury. These moons formed within circumplanetary disks surrounding their massive hosts, environments rich in gas and ice. Their origins are tied to the formation of giant planets themselves, not to catastrophic planetary collisions in the same sense proposed for Earth. The architecture of these systems reflects the differences in planetary mass and formation environment. Gas giants, with strong gravitational wells and extensive disks, readily accumulated multiple satellites. Rocky planets in the inner solar system formed within a region where material was more limited and collisions more frequent. Under those conditions, large moons are less common outcomes. Among terrestrial planets, Earth stands apart. Mercury and Venus possess no natural satellites. Mars has only its two small companions. Earth, by contrast, hosts a moon that is large relative to its planet's size, approximately 1/4 of Earth's diameter. This proportion is far greater than that seen in other rocky planet systems within our neighborhood. The consequences of this scale extend beyond visual prominence. A larger moon exerts stronger gravitational effects, influencing tides, rotation, and axial stability. In many other planetary systems within our solar system, satellites either contribute minimally to planetary dynamics or exist in configurations shaped primarily by the mass of their giant host. Earth's moon, however, participates actively in long-term evolution through ongoing exchange of angular momentum and gravitational interaction. Comparative studies suggest that such a pairing may be uncommon. Computer models of planet formation indicate that while collisions are frequent in early planetary systems, producing a large, stable satellite under the right conditions requires a specific sequence of parameters. Many impacts either fail to generate sufficient debris, produce unstable fragments, or create systems that later disperse. The endurance of a substantial moon in a relatively circular, long-lasting orbit is not guaranteed. In the broader context of planetary diversity, Earth's moon represents a distinctive outcome. It is neither a small, captured remnant nor one member of a vast retinue orbiting a giant planet. It is a singular companion to a rocky world, substantial enough to shape planetary behavior over billions of years. When viewed against this comparative backdrop, the familiarity of our moon gains new dimension. Its presence reflects a particular pathway through early solar chaos, one that diverged from the histories of neighboring planets. In that divergence lies its rarity, a quiet reminder that planetary systems do not follow identical scripts, even within the same stellar family. Long after molten oceans cooled and impact scars faded into memory, the moon remained, suspended in steady orbit. What began as debris cast outward by violence settled into rhythm. Over immense spans of time, that remnant of collision became woven into the daily experience of a living planet, not through force alone, but through repetition and constancy. Its changing phases marked the passage of nights long before written language recorded them. A thin crescent would return to fullness, then wane again, offering a visible cycle that unfolded with dependable timing. Early societies organized time around this pattern, dividing months by the moon's progression. Even the word month carries its imprint. Agricultural planning, ritual observance, and seasonal awareness were often aligned with lunar phases, embedding celestial motion into cultural structure. In mythologies across continents, the moon appeared as a symbol of renewal, fertility, guardianship, or transformation. Its regular disappearance and return suggested stories of death and rebirth. Different civilizations imagined it as a deity, a spirit, or a watchful presence guiding the night. These interpretations arose not from abstract calculation, but from observation of steady light moving predictably across dark skies. The moon's influence extended beyond gravitational interaction into the shaping of narrative and meaning. Navigation, too, drew upon its reliability. Mariners crossing open oceans learned to read the relationship between moon and tide, adjusting departure times to harness favorable currents. Before the invention of precise instruments, lunar position relative to stars assisted in estimating longitude and tracking movement across vast distances. The moon's presence in the sky provided orientation, a reference point against which journeys could be measured. While human cultures responded to its cycles, the moon continued its quieter role in planetary mechanics. Through tidal interaction, it moderated axial tilt and influenced ocean circulation. By lengthening Earth's rotation over billions of years, it contributed to the gradual shift toward longer days. These changes unfolded far beyond human awareness, yet they shaped the environmental framework within which life diversified. Its gravitational pull sculpted shorelines and nourished intertidal ecosystems. Its stabilizing effect on obliquity reduced extreme fluctuations that might have disrupted long-term climate patterns. These influences did not announce themselves dramatically. They operated continuously, each orbit reinforcing a pattern established deep in time. The word accident suggests randomness, an absence of intention. In astronomical context, collision was not guided by purpose. It followed physical law, intersecting trajectories, and exchanged momentum. Yet from that law-governed encounter emerged a configuration that proved enduring. The moon did not arrive as a companion by design, yet it became one through stability and repetition. From first light reflecting off its surface to the present moment, it has remained visible across generations. Empires rose and fell beneath its glow. Technologies advanced from stone tools to spacecraft, and still the same face returned each month. Beneath mythology and measurement lies continuity, a reminder that some structures born from chaos can persist with quiet resilience. The moon's presence above Earth is both physical and symbolic. It circles without intention, yet its motion has guided calendars, journeys, and reflections for countless cultures. Beneath these human responses, it continues its gravitational dialogue with Earth, maintaining balance while slowly drifting outward. An ancient fragment of planetary upheaval became not a fleeting remnant, but a constant companion, shaping both the mechanics of a world and the imagination of those who inhabit it. High above the shifting weather and the quiet turning of continents, the moon continues its orbit, silent and steady. It appears serene, pale light resting against darkness, yet its existence is rooted in upheaval. Long before oceans settled into basins and life traced its first patterns through water, Earth endured an encounter violent enough to erase its surface. What remains in the sky is not separate from that moment. It is the remnant of it. The young planet absorbed an impact that could have undone it entirely. Mantle material was torn free, metal sank inward, and heat enveloped the world. From that near destruction, debris circled, gathered, and condensed. Stability emerged slowly from chaos, not by intention, but through the patient shaping of gravity. The system that followed, Earth and Moon bound together, reflects both the fragility and resilience of planetary formation. When we look upward at night, we are not observing an outsider. The Moon's rock shares ancestry with Earth's crust. Isotopic signatures align. Mineral compositions echo one another. The boundary between planet and satellite is less distinct than it appears. In composition and origin, they are intertwined, two expressions of a single ancient event. The sky carries that history in visible form, though the violence itself is long gone. The quiet regularity of phases, tides, and eclipses can obscure how improbable their foundation was. A slightly altered trajectory in deep time might have yielded a different outcome. Without the precise exchange of energy and angle, debris could have escaped or fallen back or failed to gather at all. Instead, a stable orbit formed, influencing climate cycles, moderating axial tilt, and guiding ocean rhythms across billions of years. Destruction rearranged matter into partnership. The improbability of this history does not diminish its reality. Planetary systems arise from countless interactions, collisions, and dispersals. Some produce transient arrangements, others endure. That Earth and Moon settled into a long-lasting configuration capable of sustaining oceans and life underscores the delicate interplay of physics. Stability is not the absence of violence, but its transformation. The night sky holds this transformation quietly. Each time the moon rises, its surface reflects sunlight that has traveled across space, illuminating scars older than any mountain on Earth. Craters and maria preserve the record of ancient bombardment. Beneath their stillness lies evidence of the early solar system's turbulence, frozen in place. To contemplate this history is to recognize how contingent our present conditions are. Seasons unfold within narrow bounds, tides follow predictable paths, and days lengthen almost imperceptibly. All of these rhythms depend on a companion born from collision. The earth beneath our feet survived not because it avoided catastrophe, but because catastrophe reshaped it into balance. As this story draws to a close, the moon remains overhead, unchanged in appearance, yet understood more deeply. Its presence invites reflection on the thin margin between destruction and continuity, between randomness and enduring structure. If this exploration has brought a sense of quiet perspective, consider sharing it with others who find comfort in tracing the pathways of science through deep time. And as you step back into the present evening, remember that the light above carries within it the memory of chaos transformed into companionship.